Welcome to the Crypto Community Switzerland. This is a recorded Zoom meetup session.
In that case, I think I'll get started. Hang on, let me turn on the timer so that I get some feedback about the time spent. Hi, so good of the crypto community to have me again. I really enjoy preparing these talks and giving them, especially giving them. This talk actually I prepared before for a different activity, but the slides were available and I have no problems repeating it. I guess I should warn the audience that it is slightly technical in some places, and for those who are online, please feel free to interrupt me whenever. I really appreciate the opportunity to clarify. So if you've seen a talk by me before, you'll know that I like to start this kind of presentation with kind of a philosophical note, and this presentation is no different. And then the technical stuff will be after the philosophical note, and then at the end I'll offer some topics for discussion. And as usual, throughout, please interrupt me whenever you want clarification or you want to tell me I'm wrong. I can be wrong, and especially here, I'm explicit about the nature for things to be wrong here because the design space is very big, and I didn't do due diligence to make sure that what I'm presenting on the slides actually corresponds to what's happening in practice. The idea is that the big picture is correct, but the concrete instantiation may be wrong. And so you'll be left with the correct operation of the mechanics, but maybe not if you're looking for instructions for implementing. You probably need to double check what I'm saying. So let's get to the meat of the presentation. First, random garbage, philosophical note. For this part of the lecture, I decided to ask the question, why does lightning matter? And in order to motivate this, I would like to plot my position on various money-related technologies as they evolved over the last 12, 13, 14 years. Admit, all right. So the position can range from, man, not interested, to, whoa, oh my God, that's the coolest technology there is, right? And I think back in 2007, I started learning about monetary policy. This was on the heels of Ron Paul's presidential campaign. And as a result of following him, I discovered why he is critical of the Fed and how fiat money ties into all of that. And more or less simultaneously with learning about how crappy fiat money is, I learned how awesome gold is. And it's still there. Gold is still doing pretty good. And interestingly, I learned about the existence of Bitcoin pretty quickly. I think that was 2010, but then it took a while for me to actually get it. This probably happened around 2015, where I thought, well, actually, Bitcoin is not just this cool technology. It's also something that provides features that gold cannot offer. And then in 2016, 2017, I really started thinking, well, actually, it's better than gold in certain respects. And certainly, Bitcoin has more growth potential because people will understand in the future that Bitcoin has these features that gold doesn't have. You can trade in Bitcoin you can be on different parts of the world and trade essentially instantaneously, whereas with gold you have to transport it, guard your transport, take it into custody, and so on. All those things have cost associated. So why am I saying this? I'm saying this because roughly the same evolution played out with respect to lightning, except a little later. So I finished my PhD at the end of 2018, and I was still kind of lukewarm about lightning, as in, yeah, it's this nice, cool technology, but what can it really do? And it wasn't until, well, 2 years ago, really, 2000, well, really in the middle of 2020, where I started having another look at lightning, and I came to the conclusion, this technology isn't just really, really cool, it's also really, really, really useful. And my understanding about lightning has driven me to the point where I think that lightning is more important than Bitcoin, which is kind of weird because lightning requires Bitcoin to work, right? So lightning is more important than Bitcoin is a big statement, and I want to make clear what I mean by that, right? I mean, if you look at the ecosystem Bitcoin plus Lightning and take off all the Bitcoin related stuff, and you look at the ecosystem Bitcoin without Lightning, I think the first ecosystem is more valuable, bigger, better, or more concretely, its economic impact is larger. And so in the rest of this philosophical note, I will make the argument that Lightning has a bigger economical impact than Bitcoin does, at least with this restricted definition of Bitcoin and of Lightning. So in order to argue this, let's have a system theoretic look at economics. So we know that calculus is the study of functions. Functions take an input and they turn that input into an output. And that's one branch of mathematics, and the related branch is systems theory, which also takes an input and produces an output. But in addition to the output, it produces a state, and the state itself is an input also. So with the perspective on the right, we can start looking at economics. And I'd say economics is a system that transforms pieces of nature into consumables for humans, right? And we can actually look at these arrows and label them. The pieces of nature are natural resources, and the humans consume consumption goods. And this third arrow, the state arrow that feeds from the economy back into the economy, that's exactly capital. That's goods that you need to produce other goods. And with respect to this system theoretic perspective on the economy, you can articulate a metric or a benchmark to determine how effective is your economy, how well does it grow. And the key determinant with respect to that quality of the economy is capital distribution. How well is your capital allocated to producing other capital or to producing consumption goods? And in free market economies, capital owners get an incentive to redistribute that capital to more lucrative ends. And so this reallocation of capital is itself another benchmark with which to look at the quality of an economy. So the key question that I want to focus on in the context of Lightning is, how efficient is the capital reallocation that it enables? And I would say Lightning is off the charts. So with respect to capital reallocation, you can ask the question, what are the obstacles towards capital reallocation, and how do various money candidates resist those obstacles? And I came up with a couple of potential obstacles, like you have to trust someone who holds the asset on your behalf, or transferring the asset is difficult, or owning the asset is difficult because the state doesn't really the state policy of ownership of that asset can be bad for capital reallocation, or they can intervene without having a articulated policy. And then time is itself another obstacle towards capital reallocation. And then a third thing is scale. Just because you can move a tiny bit of capital doesn't mean you can move a lot of capital. So with respect to those possible obstacles, we can have a look at credit or fiat. We can have a look at gold, Bitcoin, and Lightning. With respect to the first column, I decided to omit cash. And if you omit cash, then credit and fiat do not have finality at all. You always trust that the money is on the bank, and if you don't trust the banks, you're screwed. It is actually very easy to transfer fiat, but then the monetary policy sucks, and if the government wants to intervene, they can. And well, sometimes you can transfer fiat money really, really quickly, but then if you try to transfer it to another country, it can get stuck. You have to phone banks. The banks accuse each other of sitting on the money. It's a bit of a hassle. But then on the other hand, in terms of scale, it scales really, really well because it's a centralized system. Gold, on the other hand, has excellent trust/finality properties, but it's kind of difficult to transfer because you have to transport it. You have to pay armed guards to transport it. You have to take it into custody. You have to assay it when you take it into custody, and so on. So that's actually not optimal. In terms of monetary policy, it's been the root of the monetary policy for thousands of years, and it's difficult to produce more gold. And so I'd say the monetary policy is pretty good, but that's my subjective sense of what good monetary policy is. I'd say another aspect where gold is suboptimal is in terms of state intervention. The state can come in, it can stop gold at the borders and even confiscate gold within borders. And so I'd have to say that's a failure of the gold standard. And then with respect to time, it takes a while for the gold to physically travel from one location to another, especially if it's a large quantity of gold. On the other hand, in terms of scale, the problem isn't so big because 1 ounce of gold can be transferred between two parties, and that transfer doesn't prevent another ounce of gold between two other parties from being transferred. Now, Bitcoin has lots more green check marks. We all know the many, many virtues of Bitcoin, but the big vice in my eyes is its lack of scalability. This comes from the blockchain having a limited capacity for transactions. One transaction between two parties on the Bitcoin blockchain is preventing another transaction on the same blockchain from being confirmed. And therefore, the capacity of Bitcoin to reallocate capital is limited. Lightning fixes this. Lightning inherits all the positive qualities of Bitcoin, and it's super fast, whereas Bitcoin is just okayishly fast. And most of all, most importantly, one Lightning transaction does not prevent another Lightning transaction from being confirmed. That's a big deal. That's a big deal. To illustrate how big of a deal that is, let's draw a histogram. Hello?
I have a question.
Yes.
You said Lightning has big scale, but the Lightning Network at the moment only has 1,500 BTC. So you cannot argue that it can scale unless a lot more Bitcoin is pumped into the Lightning Network. Won't you say so?
Scale can mean different things. Scale can mean it can allow many, many, many small transactions or it can allow really, really large transactions. And I'd say Lightning does not scale very well with respect to large transactions. With respect to large transactions, I'd actually say Bitcoin scales better. But when it comes to number of transactions and small transactions especially, Lightning does scale.
That makes sense. Yeah, thanks.
And so we can visualize the effect that Lightning has on capital in terms of how easy it is to reallocate that capital. So let's draw a histogram of all the capital in the world in various universes. And in the first universe, we just have fiat. And on the lower end of the bell curve, I imagine that it would be a bell curve, but I'm actually not sure. On the lower end of the bell curve, we would have something like houses, cars, right? If you want to, you do need them, but if you want to turn it into something else, then it's rather difficult because you have to take out a mortgage on your house, or you have to find a buyer for your house, and they have to determine how valuable your house is, and so on. So it's really a big hassle, and it takes a lot of time for you to turn your house into something that you can use to produce goods later on in the economy. And then on the super high end of the bell curve, I expect you would see something like high frequency trading, where the money is reallocated from one resource to another resource in a matter of milliseconds. And then I imagine that a lot of money is somewhere in between, not quite as difficult to repurpose as houses, but not quite as easy as high frequency trading. And then I imagine that Bitcoin, or rather the world with fiat and Bitcoin, is strictly better than the world with just fiat. And in terms of the distribution or the histogram of capital, well, whenever you have an option, you have one more option because now Bitcoin exists also. And you can put a lot of capital into Bitcoin, and Bitcoin is more fluid. It's uncensorable, it's difficult to stop. And so Bitcoin does make, or putting a portion of your assets into Bitcoin makes your entire portfolio more reallocatable, or makes it easier to reallocate your portfolio. And then the reason why I drew this graph of Bitcoin so close to the graph of fiat is because Bitcoin doesn't really have good scalability. Now, the first time I gave this presentation, someone made the same argument that Ralph just made. Bitcoin does have scalability in terms of the quantity within one transaction. You can transfer millions of Bitcoins if there's ever millions of Bitcoins inside of one address. So there is no limitation to how much capital can be moved around, but there is a limitation to how many transactions can affect that movement of capital. And there's also a limitation to the time that it takes for that movement of capital or that reallocation of capital to take effect. And with respect to those latter 2 points, I'd have to say that Lightning fixes this. The transactions that Lightning enables, they can be millions of transactions per millisecond. There is literally no limit to the number of transactions that Lightning enables. And it's lightning fast. That's where the name comes from. And so I would have to say there's no link anymore between the graph of Lightning and the graph of fiat. So,
sorry, have there been any sort of experiments being done in practice about the scalability aspect of Lightning? So the number of transactions per second. When you say it could be kind of a infinite number, it would still be interesting to see whether in reality this has been achieved to some extent.
Well, I don't see where any limitation could come from physically. the whole point is if you and I have a Lightning channel and Alice and Bob have a Lightning channel, we can update our Lightning channel as often as we like, and they can update their Lightning channel as often as they like, and our activity does not interfere with their activity and vice versa.
But is there any chance of knowing how many transactions are being done in the network?
Well, I guess you could compute make an estimation about the number of CPUs in the world, and you could make an estimation if they were all simultaneously signing Bitcoin transactions, the kind of Bitcoin transactions that you need to make Lightning transactions. Then there is a hard upper bound you can derive for the number of Lightning transactions per time unit. But I don't think we're ever going to come anywhere near that hard upper bound in terms of capacity, because there are a lot of CPUs out there in the world, and well, we also want to use them for other things than Lightning transactions. Yes,
of course. But my question was more, is it easy to, with Bitcoin, there's this on-chain transaction insights that you can get. You know how many transactions are done on the Bitcoin network. Is it similarly on the Lightning network possible to see transparently how many transactions are effectively done?
No, you cannot see this.
Okay.
The reason why you cannot see this is because you cannot see into the computers of participants on the Lightning network. So Alice and Bob might have a Lightning channel, or they might have they might be participating on the network, but unless you can see their RAM, you would not be able to know how much they are sending back and forth.
So it's much more anonymous than the Bitcoin network then?
Yes, absolutely.
Okay, thanks.
All right. Yeah, so this picture summarizes why I think more highly of Lightning than I think of Bitcoin. Or I do realize, of course, that Lightning requires Bitcoin to work, but my position is rather the economic impact of Lightning, I think, is bigger than the economic impact of Bitcoin without Lightning. All right. With all that said, let's get into some technical details, starting with terminology. And unfortunately, terminology is different depending on your source. So let me, in this slide, fix some terminology for the purpose of this presentation. So a payment channel is a protocol between two nodes on the network who record a balance, which is a debt. That you can think of this as a splitwise debt. Alice bought groceries, Bob bought dinner this evening, and now they need to settle their debt, or they don't need to settle it, they just need to record it. So that kind of balance is being maintained, but they're never actually touching the chain except at the start and at the end. So they're recording this balance off the chain. That's a payment channel. And then when you have a collection of these payment channels, all between participants who record the balance off chain, then you can actually describe it as a network of payment channels, and that's a payment channel network. All right. And then the idea is that you'll be able to pay or receive payment from anyone in the network that you're connected to. And so you could use intermediaries to forward your payment or to forward a payment to you. And those intermediaries are called hops. And then an atomic lock consists of two parts. Atomic means that either the, excuse me, it means that either the entire payment goes through or nothing goes through. And the lock means it's a balance update that is going to be confirmed, or that might be confirmed in the future, but it's not final yet. And so the way this is going to work is the same payment here is going to be made, but it's going to happen in stages. The first stage, we're going to put into place locks. These are payments that are waiting to be confirmed. And then once all the locks are in place, they are all activated simultaneously, and then the payment has happened. So atomic refers to the fact that the transformation of green into blue cannot happen halfway and then stop. It either happens entirely or it doesn't happen at all. And then lightning, I would define, and sadly, papers that write about lightning define it differently. I would define lightning as a technology for atomic multi-hop payments across a payment channel network. So in particular, all these various alternatives like Bolt, L2, Raiden, Blitz, anonymous multi-hop locks, in my lexicon, they're all part of Lightning. They're all Lightning technologies. And that's part of the problem. Only Bolt describes itself as Lightning. All the others describe itself as something else. And I think that's wrong. But yeah, who am I to decide? So let's see how it works. There are two basic technological components. And before I get there, let me reiterate, take what I say with a grain of salt. The answers are probably not 100% correct if you get into the details. So if you want to implement a Lightning node based off of this presentation, you probably want to double check what I say and check with the original sources. On the other hand, this presentation does ask the right questions and does convey the intuition behind the answers, or at least that's the intention. So in particular, what I'm going to describe is closer to L2, which is the improvement that Christian Decker and others have proposed that relies on a new Bitcoin script opcode that does not exist in Bitcoin currently. Nevertheless, maybe someday it might, and so I'm going to describe that instead. This opcode is not included in the Taproot update, sadly. All right, so the idea behind the Lightning channel is Alice and Bob put in Bitcoins, and then they update this mutual balance of Bitcoins several times. And then at some point they decide to close the channel, and that means they retrieve their Bitcoins from the channel. And the idea is that they only have to touch the blockchain once at the start to put the Bitcoins onto the channel, and a second time at the end to take their Bitcoin off of the channel. But in between opening the channel and closing it, they can update the balance any number of times. And they do this just privately, talking between themselves. They don't have to inform anyone else that this balance is being updated. And the question is, how do we achieve this? There are two technological components. And the first one is the hash time lock contract. But before I get there, let's look at transactions. So this is a visual depiction of a Bitcoin transaction. So the incoming unspent transaction outputs, or UTXOs, need to be unlocked by a transaction. And the transaction, in order to unlock those UTXOs, provides witnesses. And I use witnesses as a second word and sigma as the first witness. Sigma refers to the fact that it's a signature. Not all witnesses are signatures, but all signatures are witnesses. And then the transaction produces new unspent transaction outputs, UTXOs, which themselves again need witnesses to be unlocked by the next transaction. And so I'll use sigma in gray on the arrow, even though it wasn't provided yet, just to clarify that it's going to be a signature witness, and I'll use a gray dot to indicate that it's going to be something else. So this is a transaction, and this is a multi-sig transaction. So it's, however the money came there, the output of this transaction is a single unspent transaction output, UTXO, that can be unlocked only if you provide two signatures, one that is valid under Alice's public key and one that is valid under Bob's public key. Note that they must both sign the transaction TX, which is not the transaction on the left, but that's the transaction on the right that I didn't draw here. It's the next transaction that these signatures sign. All right. So the first ingredient for a Lightning channel is the funding transaction, which is basically the same as a multi-sig transaction. It is possible to close this channel, but that closure needs a signature from Alice and a signature from Bob on whatever transaction spends this UTXO. And that's called a mutual close. So whenever Alice and Bob agree, they can spend the funding transaction, or they can spend the money as they see fit. Very good. All right. That is, however, just one possible way in which they spend the money. There are other ways, and this is the key thing. So the mutual close, that's always available, but there's another option that's available even when the counterparty is offline. So suppose Alice and Bob have agreed on a particular balance, and then Alice wants to use those Bitcoins for something else, and Bob is not responding. So in particular, Bob cannot produce the signature that would allow the mutual close transaction to occur. So what does Alice do then? Well, what she does is she publishes two transactions, the disputable transaction and the settlement transaction. And these transactions are linked, right? The disputable transaction includes a counter, and the settlement transaction refers to the disputable transaction with the same counter. And I should mention, in order to spend the funding transaction to a disputable transaction, Alice provides the signature as well as a signature from Bob on the hash of the disputable transaction. So Alice already received that signature on the hash of the disputable transaction in the past, and she's sitting on that data waiting to use it if she needs to. And likewise, Bob has Alice's signature on the hash of the disputable transaction in case he needs it. So Alice wants to close the channel without interacting with Bob. Fair enough. She publishes this disputable transaction. She already has Bob's signature on the hash of the disputable transaction. She generates her own signature on the disputable transaction, and then the disputable transaction will end up being confirmed by the blockchain. The disputable transaction can be spent by the settlement transaction if the settlement transaction has the same counter and if it has a time difference. So the disputable transaction is confirmed before the time window has elapsed, any block that confirms the settlement transaction is invalid. And so blocks won't include it. And this gives Bob a time window in which he can say, well, actually, this is not the latest state of the channel. And so that's what's explained on this slide. Alice, either mistakenly or maliciously, decided to close the channel to a balance that is stale, that is old. In the meantime, Bob has received a balance surplus that Alice is now trying to cheat him out of. And that's what the time window delta t is for. So the disputable transaction was confirmed, the settlement transaction not. So Bob contests this close by publishing the most recent settlement transaction. And the fact that this settlement transaction follows a disputable transaction whose counter is smaller instead of the same allows Bob to bypass this time window. So when the disputable transaction is published, Alice needs to wait delta t time, which could be 5 hours, it could be 1 week, before the settlement in her favor is confirmed. Whereas Bob, if he's online, can immediately confirm the balance in his favor. So that's called a contested close. And the reason why Bob cannot always publish this, or in other words, when Alice is being honest, Bob cannot publish this settlement transaction. He cannot publish it to an older one in his favor because the counter of the settlement transaction isn't going to be bigger than the counter of the disputable transaction. So Bob will only be able to force a close to a balance that occurred later. All right. So,
you have to admit this is highly complicated.
yeah. Feel free to ask a question or ask for clarification anywhere.
I would not know where to start. No, it's okay. Thank you.
Here's another way of trying to explain the same thing. We can look at the distribution of information and which pieces of information are needed to effect which type of channel closure. So, as always, Alice and Bob both have a secret key and they know each other's public keys. So the public keys are public knowledge and the secret keys are secret. And this does not correspond to any closure event. In addition to that, they have they have agreed to a mutual balance, and that essentially consists of UTXOs that are unlockable by their public keys, or rather by their signatures. And in addition to those UTXOs, there is the counterparty signature on the hash of the disputable transaction and the counterparty signature on the settlement transaction, right? This is what they need in order to effect a unilateral close. So exactly, this is the information that Alice needs in order to effect a unilateral close. She also needs to generate a signature, and that's why I also circled with a dotted blue line Alice's secret key. And so when Alice publishes that disputable transaction, she publishes that signature because otherwise it will not be confirmed. All right, fair enough. What happens if in the meantime the state is updated, right? Alice pays Bob or Bob pays Alice and they agree to update their balance. Well, that means there is a new pair of UTXOs and there is a new pair of counterparty signatures, which they need to effect a unilateral change. But if both of these things happen, if there is a state update and a unilateral close of an old state, well, now Bob has all the information he needs to contest this unilateral close, because the missing piece was the signature from Alice on the disputable transaction, which she should never have published, because the disputable transaction fixes the balance that she closes to, and it was not the most recent state. It was not the most recent balance that she signed. And that missing piece of information is what allows Bob to contest this unilateral close and to close the channel to a more recent state. All right. That's
one question.
Yes.
One question, Alan. Is there any penalty for nodes that, let's say, try to issue transactions that then get contested?
Currently on the Bitcoin Lightning Network, the answer is yes. So what I'm describing here is closer to L2, where you can only close the channel to a more recent state if you're contesting the closure. The way Bitcoin Lightning Network does it, or rather the Lightning Network that's currently deployed, the way they do it there is if Alice tries to cheat Bob and Bob contests, then Alice loses everything.
Okay, thank you.
I think both strategies have merit. Okay, so that's one of the ingredients. That's the mechanics of the channel between Alice and Bob. But what happens if you have a series of channels, Alice, Bob, Charlie, and David, and Alice wants to pay David? How do you make a payment from Alice to David atomic? And the answer is the hash time lock contract. So David, the receiver, generates a random bit string and hashes it to produce the digest H. And H goes to Alice. And Alice makes a promise to Bob: I will pay you if you provide me with a pre-image R that hashes to the digest H. And Bob says, okay, thanks, I'll try. And of course, reversing the hash is impossible. So the only way Bob is going to get anything at all is if he forwards the promise to Charlie: I will pay you if you give me this pre-image R that hashes to the digest H. And Charlie is in the same situation, so he might as well forward the promise to David, and David is the one who produced this hash. So he could say, okay, here is R, give me my payment. And likewise, Charlie now has R, so Charlie can say, here it is, give me my payment. And Bob can say, here it is, give me my payment. And in the end, Alice obtains R, and then R is the proof of payment. And the reason why this is atomic is because if at any point where R is propagating backwards along the line of payment, if any one of these nodes is being unresponsive, in this case, David will close the channel using a special payment path that involves R, and that allows him to close the channel to the balance that is in his favor, that incorporates this payment. That channel closure will contain the value R. And since all the other participants observe the state of the blockchain, they will learn R as well. So David and Charlie and Bob, they all are in a position to close this channel forcefully because they possess R. But they don't need to. They can convince the party earlier on in the payment path to cooperate and update the channel balance without having to publish a transaction to the blockchain. So how do we integrate this mechanism with the channel mechanism that I described earlier? The answer is hash time lock contract. And it's very simple. I've already described the hash part. There's also a time lock part. So this is the picture of a few slides ago. And we're going to add a new payment path. And this is the HTLC is just another disputable transaction that comes with another settlement transaction. And the only difference is this third line of conditions under which the arrow goes through. The hash time lock contract, or the hash time lock contract transaction, it has to provide the hash preimage R that hashes to H, and it can only be activated before a certain timeout window. And so Alice can say, Bob, okay, here is a hash time lock contract, all the information you need, and please provide me with R, and then we can update, or you can require, or you can effect this channel update on chain. And then Bob responds, okay, here is R. Let's update this channel before the timeout is over, because otherwise I will publish this transaction and close the channel, and I will still get my money, and we won't have a channel anymore. And so it's in Alice's best interest to agree to the off-chain channel update. And if Alice does, then, well, after the timeout, this payment path will have become impossible. But in the meantime, Alice and Bob will have shared the counterparty signatures that enable the unilateral close again. So that's Lightning in a nutshell. Let's have a look at a few attacks. In fact, there are two attacks on Lightning that have been identified in the meantime, or rather two attacks that have reached the academic community. And the one attack is the wormhole attack. And the idea is the sender generates a circuit to receive, or to send a payment to the receiver, but unbeknownst to the sender, one of the hops, or two of the hops on his circuit, is actually the same node, and they send the funds along the shorter path that the sender doesn't know was available. And as a result of this shortcut, the nodes on the long end of the path, they still expect the payment to happen, but it actually won't ever happen. So the colluding nodes, they can steal the fees, and that's not a super big problem, but they leave the skipped intermediaries hanging, and that's a bigger problem. All right, that's one attack. And then another attack is the exact opposite. It's where the sender is the attacker, and instead of sending his money through the shortest path to the receiver, he sends his money through the longest path to the receiver. And in doing that, he is causing the network to lock up funds waiting for activation. And it can take a while before this activation happens, or perhaps it's never activated, and then it automatically expires, but it takes a while before that expiration takes place. So the sender immobilizes the network through this griefing attack. All right, those were two attacks. And another thing that academics are really, yes, go ahead.
These two attacks are not solved yet. They exist.
I'm afraid I cannot hear you.
Sorry. Are these two attacks solved, or they still exist?
The paper that I'm going to talk about right now, it solves the wormhole attack. I'm not sure about the griefing attack. The nature of these attacks is well, certainly of the griefing attack is that it's difficult to defend against. And well, I'll get back to this point later, because the solution that's presented here protects against Lightning attacks, but enables griefing attacks, whereas the naive solution protects against griefing attacks, but not against wormhole attacks. And so, yeah, it's difficult because it seems that you have to pick one out of two. The current Bitcoin Lightning Network does not incorporate this solution. It is susceptible to the wormhole attack. In principle, it can defend against the griefing attack, but I don't think it does. The reason why it can defend against the griefing attack is because the same hash preimage R is used across the entire payment. And so it's very easy for nodes to detect that they're being griefed. But as far as I know, they don't detect this, but it's not too difficult to protect against it. All right, so anonymous multi-hop blocks is essentially using homomorphic functions to do hash time lock contracts. So this is a paper, and I think is an excellent paper. It has 3 big contributions, one of which is the wormhole attack, which I covered a few slides back. Another one is a security definition in the UC framework. And this UC framework is what makes cryptographers really, really enthusiastic, because it's a strategy for proving the security of arbitrary protocols. And I'm not going to bore you to death with the security proof. I'm going to focus on the 3rd contribution of this paper, which is the realization of Lightning using homomorphic primitives. So what is a homomorphic primitive? It's a function that allows an operation such as addition to move outside of the brackets. So G applied to the sum of A and B equals the sum of G applied to A and G applied to B. So whenever you see this kind of magic algebra, homomorphism is probably the right description. And this is, by the way, exactly the kind of structure that hash functions are designed to make either impossible or difficult to find. But instead of using hash functions, this particular construction is going to use functions that actually exhibit this, that make it easy to use this property. And so you can think of exponentiation solves this, or addition on elliptic curve points, they satisfy this relation. And in fact, the Taproot protocol upgrade enables payment points, which is essentially the construction that I'm going to describe right now. So instead of the hash function H, we're going to use the homomorphic one-way function G. And what the receiver does is he selects a random K and applies the homomorphic one-way function G to K and sends that result to the sender. And the sender chooses random values Y1 and Y2 and distributes Y1 and Y2 to all intermediaries, and every intermediary receives one of these random values. And in addition to that, the intermediary receives G applied to consecutive sums. And then in the last step, the sender sends to the receiver the sum of these random Y values. Okay, so the receiver then sends the sum of the secret values, which he received, to Charlie, and this unlocks one of the pre-image puzzles. And in addition to that, Charlie can subtract. This meeting is being recorded. Very good. Bob receives the secret value and can subtract it from what he received, or he can subtract what he received from the secret value and send it to the sender. And so the same pre-image puzzle is in effect, because they all unlock a certain function of x equals y type puzzle. But because of because of the fact that this function is homomorphic, they all see different images. And this actually improves privacy quite a lot because they cannot know that they are part of the same payment circuit, because the images that they are receiving are different. And so the question would be, how do you integrate this enhanced construction with Lightning channels? And that's exactly what the adapter signature does. An adapter signature is just a signature scheme plus a pre-image puzzle. And if your signature scheme uses elliptic curve Schnorr, as Taproot will enable, then you can use elliptic curve Schnorr adapter signature scheme to do signatures in addition to this exact pre-image puzzle. All right. So that's one result that I'm very, very happy with. And then there's another paper that came out very recently that I also find absolutely fantastic. It's called Blitz. And this is another example of people doing Lightning research and calling their stuff something different from Lightning. I think it's Lightning. It's just another paradigm, in fact, for payments. So they invent here the pay or revoke paradigm, and it fits squarely in the Venn intersection of two already existing paradigms, one of which would be lock and release, and the third one of which would be hope and pray. So the big advantage of lock and release is that you build your entire payment circuit and you lock everything into place. And then when you activate the payment, it goes through entirely or not at all. And that's the atomicity property of the payment. And that's what lock and release is really, really good at. The disadvantage is that you have to go back and forth, or forth and back, right? The pre-image propagates backward through the payment path. And that takes a while. And maybe you don't want to wait so long. And if you really don't want to wait so long, the other paradigm for forwarding payments across a payment channel network is hope and pray. You send your money to Bob, and then you forget about it, and you hope and pray that Bob sends his money to Charlie, and Charlie to David. And if you hope hard enough, the money will land with the intended recipient. This is pretty terrible in terms of security, because hoping doesn't really work, and neither does trusting, but at least it has a one-pass mechanism. After you send out the payment, you don't have to wait anymore. And so what pay or revoke does, it actually recycles these two selling points from these payment paradigms. It is definitely atomic, and in some cases, it is also one pass. Now, I think they market the one pass property a little too much, and that's why I added the asterisk there. So let's see how it works. Once again, we have a payment circuit from Alice to Bob, Charlie, and David. Alice is the sender, David is the receiver. And what's going to happen is, I'm going to describe this in the hash time lock construction that I already described earlier. So Alice chooses a random string of bits, R, hashes it, obtains the digest H, and makes a provisional payment to Bob. This payment is provisional because it will go through by default, but it can be revoked. And Bob forwards this payment to Charlie, Charlie to David, and David actually signs a message confirming that the payment was received. And this signature confirming that the payment was received locks everything in place, just like the hash pre-image did earlier. The signature can propagate backwards, and it makes it such that the revocation, which was possible earlier, now definitely cannot happen. And then as long as the signature hasn't finalized the transaction, Alice can, in principle, release R, and R revokes the transaction. So then the question is, how do we integrate this mechanism with Lightning channels? And I described it here in terms of hash time lock contracts, and that's totally, definitely possible. But in the paper, they actually find a new construction altogether using the enable refund transaction, which atomically refunds everything because everybody signed this batch of transactions. I find this one, the way I presented it, I find it more intuitive and simpler too, but there are definite advantages to this enable refund transaction that I'm not going to get into here. And so we can compare these two models of transactions. So on the one hand, we have the contract-based Lightning channels, and on the other hand, we have the revocable, I shouldn't say Lightning channels, these are these revocable payment channel network payments. And when it's contract-based, it is through lock and release. You lock a series of promises into effect, and then you release everything in one go. Whereas the revocable payments, the payment goes through by default, and it can be confirmed if you want a fast confirmation, but if it's not confirmed and it's not revoked, it will go through by default. But in exchange, it might be revoked. So both are definitely atomic. They either go through or they don't, and nobody is left hanging, or nobody is risking being left hanging. And there are various ways to achieve this. So the HTLC, hash time lock contract, is how the contract-based payment does work, and the homomorphic one-way function is how the atomic multi-op locks proposed for it to work. And I'm pretty sure that you can find a similar construction to the enable refund transaction that works for the contract-based case. And I'm also pretty sure that you can find a homomorphic one-way function-based construction that works in the revocable model of transactions. But I don't think that exists yet. And I'd say they are both two-pass. Why is the revocable payment two-pass? Well, it's because the fast transaction needs the receiver to sign and lock everything into place. And that signature propagates backwards through the payment channel, through the payment circuit, just the same as the hash preimage does in the contract-based payment. So I'd say in the revocable case, it's two-pass in 99% of the time, and this 1% of the time when one of the nodes is being inactive, it actually survives despite having only one pass because the payment goes through by default. The difference is what happens if there is only one phase because one of the nodes is behaving maliciously or not responding. And in the contract-based payment, the default is the payment will be reverted, whereas in the revocable payment, in the revocable case, one phase only means the payment will be confirmed. And that means that the contract-based payment is not very friendly to offline receivers because they have to be active. And if they're not active, the payment will be reverted. On the other hand, the revocable payment is friendly to offline receivers because they don't have to sign and they can still receive the payment. And I think that's okay. In both cases, there are selling points for having both of these systems. So that's nice. All right. That was the big overview of the technical stuff, and then here follow some points for discussion. While making these slides, I came to the conclusion that the construction of Lightning channels is a very, very, very subtle thing. And I'd say the design space is underexplored. All of the existing proposals lie very, very close, and there is no limitation to how widely you can start exploring this space. And I drew here 4 examples of Lightning technology, and I would even have to say that the concrete transaction models that I came up with for the purpose of these slides, they have to be something else. So the design space is huge, and it's easy for different people to design something that achieves the same thing in different ways, in such a way that they will actually end up speaking a different protocol. So it's important to have good standards here. And it's also really easy to screw up. And that makes me skeptical about any security argument that would be leveled to make an argument that these things are not risking your money. And that this is one of the reasons why I was so happy with the proof in the universal composability model. I mean, I think that's a very big achievement of that paper. Lastly, I would look very positively if people were to design tools for designing Lightning type protocols automatically, and that take this security into automatic construction. Perhaps even something that doesn't compile if there isn't a proof of security attached to your code or something like that. I would receive that very, very warmly. Another point
Alan, one question.
Yes?
One question on the previous slide. So here you focus the security argument, and I think you didn't mention it yet, but how centralized is currently the Lightning network? Like the level of centralization compared to for instance, Bitcoin.
Well, everyone who is on Lightning is on Bitcoin.
Mm-hmm.
So I'd say the Lightning network is necessarily less decentralized or more centralized than the Bitcoin
Mm-hmm.
network.
But to a degree that, you know, in terms of security, one big question that I had when I came to this session was exactly to understand, will you touch it further to understand this centralization versus Bitcoin? Or
in my eyes, centralization, decentralization is not really a security aspect. I mean,
no.
Yes, you could say we want to consider that too, but what I meant by this bullet point on this slide is in terms of cryptographic security, what hard problems are involved? Does the attacker need to solve a hard problem before he can steal your funds? That kind of question. I'd say those questions are orthogonal to questions of, is there enough capital spread out over enough different people who are active on the network type of crypto economic security guarantees.
Okay, thank you.
I think this is the last remark I want to make, which relates to forms of consensus algorithms. So we were speaking about Bitcoin most of the time, and Bitcoin uses Nakamoto consensus, which you can think of as a funnel that takes in various distinct perspectives on the set of transactions that are valid and outputs a single agreed upon set of transactions that are valid. Now, if you're willing to entertain a departure from this model, then I would suggest having a look at NC Max. NC stands for Nakamoto consensus, which splits this procedure into 2 parts. In the first part, one problem is solved, which is the dissemination of the transactions. So the blocks actually contain transactions, but they don't have to be valid. They can be mutually incompatible or just plain wrong. And in the second part, blocks also confirm transactions. So the key point is that the transactions that are announced can only be confirmed several blocks later, so that downloading new transactions cannot be the bottleneck for propagating blocks. And as a result of this pipelined movement, NC Max argues that there is actually a much bigger throughput of transactions on their network. So this is the flagship consensus protocol of the Nervos network. And I'd say the second consensus protocol is actually, so it solves the consensus in 2 steps. It solves communication and validation of transactions separately. And I'd say this is very reminiscent to me of law, where you file suit and later on the judge renders judgment. And in the meantime, you have this process whereby you gather evidence, you ask your counterparty, please provide us with these documents, and it goes back and forth. It goes back and forth until all the data is in, all the evidence is in, then the judge renders judgment. And just as that works in a staged process, so too do I think that the judgment about disputable transactions can follow this pipelined approach, where you announce your intention to close this channel and the state to which you want to close it to the world in the first stage, and that gives the counterparty the option to dispute this transaction before it is actually validated. And with respect to this disputation queue and disputation period, there might be more back and forth than I just described in the Lightning channel, particularly if you have contracts that have very complicated evolutions. You might want to need several rounds of back and forth before you've come to the point where you can actually render judgment, or before you come to the point where the blockchain renders judgment for you in favor of one settlement transaction or the other. And that raises an interesting question. How can you integrate this information into the Lightning transactions? For instance, if the fees are high, maybe you want the disputation window to be larger. So is it possible to integrate information about the fees into your Lightning transactions? That would be a dynamic dispute resolution policy, and people are also researching that. I think that was my last slide. So thank you for the attention, and I'm happy to take any questions.
But I'll go back a little bit again to the security part, because one thing that I was hoping to understand regarding the security is, for instance, the reliability that I perceive from the Bitcoin is, for instance, this 51% attack is what is needed to let's say challenge the network or challenge the consensus. And I was trying to understand from the side of the Lightning, what would it be? So it's like a mesh or like a network within a network, right?
Yes.
So then on that second layer, how does the consensus can be compromised? I was trying to understand a little bit better, and I didn't took it yet from the presentation.
The consensus is identical to that of Bitcoin. And so if there is an attack on Bitcoin consensus, it will undermine Lightning also.
But my point is, at what level there can be a consensus within the Lightning that compromises the transactions within the Lightning, but doesn't require, that doesn't compromise the Bitcoin. like how further compromised can Lightning be?
I'm not sure I understand
No,
this question.
so I was trying to explain it in the terms of for the Bitcoin can be compromised if we have a 51% attack within the Bitcoin. Okay, but then this is a network on top of that network. So there's let's say a different set of nodes, a subset of nodes from the existing ones, right? Within those subset of nodes, there's a different protocol.
Yes.
Correct? Extended protocol. That extended protocol needs to have another level of consensus, right? Needs to have another consensus within the protocol. And my point is not a proof of work, or if it's a proof of work, is also a 51% within that subset or not?
Hang on. The nodes in this overlay network do not have another form of consensus. They observe the Bitcoin blockchain, and the only thing they need to agree about is the state of the Bitcoin blockchain. So they use the same consensus mechanism that Bitcoin already uses, and they don't use anything extra.
Okay, so there might be a misunderstanding from my side, but for instance, these channels that you were describing, so I enter in a channel, and by entering in a channel, I become a node on this overlay, correct?
You enter into a channel with someone.
With
There's
someone.
always a counterparty to your channel.
And that someone as another is with in counterparty to with someone else. Therefore, I'm in counterparty with the contacts of that person, correct?
Yes.
So that's how the second this second layer or this overlay builds. My point is, for that to keep a consensus among, there's not let's say a constant transaction in the Bitcoin, the main chain, for each one that is exchanging on this overlay. For each transaction on the overlay, there's not a corresponding transaction on the main chain, correct?
Correct.
So at this level, now we're talking about on this, let's say, transactions on the overlay. How this consensus for these sub transactions works? That was a little bit more.
Consensus is you need consensus about the ledger of transactions in Bitcoin because if people disagree, then they can't agree on how many Bitcoins you have, and they can't agree that a payment you make is valid. There is consensus. There's still consensus, even if there is a Lightning network, about the transactions on the Bitcoin blockchain. And so everybody who audits the Bitcoin blockchain will be able to determine the total amount of Bitcoins locked in every Lightning channel.
Okay, exactly. But the split
within the inspect in those Lightning channels to determine the relative balances.
And that's I was trying to understand within those Lightning channels, how does the consensus form around? And that's what I was trying to get from your presentation. So I was trying to get what is the consensus there? What makes, you know, among that overlay?
There's nothing to attain consensus about.
If I transfer something to Alice, or if I transfer something for Alice contacts, as you were describing through this presentation, let's say there's a consensus solution needed, right? All the nodes within this overlay need to be agreeing. No. So maybe that's where I think I missed the point. Like, my understanding might be limited, and I understood it via, let's say, that the blockchain will, by reaching consensus, it's what makes it work. And I was trying to understand what would be the consensus part, what makes it work on the Lightning for these transfers of money within the overlay.
The only thing Alice cares about is that in the checkbook that she shares with Bob, her balance has increased as a result of your actions.
And that is via these signatures that you were explaining, right?
Yes.
So she signs, and then she forces the other one to sign as well, and she holds the previous signature in case that she needs to cancel the transaction. But I still miss that just with the signatures. So let's say Bitcoin would not do it only via signatures. Every single time that the thing needs to be registered in the ledger, I was seeing these transactions being registered somewhere and needed a consensus on the current status between, let's say, Bob and Alice, or Bob and some other partner. Because I'm still missing, or maybe it's a misunderstanding from me, there must be a sub-ledger for the Lightning, correct?
No, there isn't.
I know, there isn't. So it's just all these transactions get aggregated and sign each other and become like one single transaction afterwards into the main blockchain. So it's just one transaction for a channel.
Correct.
And within this block of transactions that happen on the overlay, there's no consensus. So it's just like a Merkle tree kind of thing. Like,
there are no Merkle trees involved.
okay.
And the point is, if you and I share a channel, if there was ever lack of consensus about our channel balance, meaning that you and I disagree, then we would instantly close the channel and settle the difference there then and then. So there is an implicit pairwise consensus.
I see. So it's like you keep transacting, and by transacting, you are assuming consensus on the previous state, more or less.
Correct.
So by giving another transaction, you're validating the previous one between that channel?
Yes. There is no cryptographic link to the previous one, but it only makes sense to apply the balance update to a previous balance.
But you see my line of rationale. So I'm feeling that I'm missing something on the Lightning to really understand it, because I come from a different side, not so mathematical. So I'm seeing it a little bit from my limitation with the, like, what is the difference? You know, I think I didn't grasp it fully as you were explaining it, but I'm kind of let's say confused on this point here. Like, am I building a new ledger within this overlay, or no, this channel is just like
it's much more similar to a tab that you might have at the bar, right? Because if you want to pay by credit card at a cafe, the bartender won't like you because he's losing 3 cents off of every transaction. But if instead you order the entire evening and settle the tab at the end of the evening in only one credit card transaction, then the bartender will be a lot happier because he's losing these 3 cents only once. And there doesn't need to be consensus about your bar tab at every restaurant. The only thing you care about is that you can dine anywhere you like. So translated to Lightning, that means that you are in credit in the eyes of all of these channels that you are a party to.
Yeah, but I still see it that at any given time, all my Bitcoins that are currently locked within the channel are, let's say, I was trying to understand, are they out of my security? Are they out of my control or not? So how risky is it?
Your control, because you can always close the channel to the most recent state. And if you behave honestly, you will not lose any Bitcoins.
So for any transaction that was done, okay, so that basically on that channel, I can close it at any given time. I use the last transaction, and that should be closing the channel. Correct. If someone tried to kind of, then we go into the attacks that you were describing, and those are kind of the weaknesses of that channel in terms of the transactions that happened, right?
Correct.
And can someone, let's say we are on the honest transaction, but one party unilaterally can initiate a transaction, let's say?
No, because hang on, they cannot unilaterally initiate a transaction, because if that action results in disagreement, about the balance, then you will still be able to close to what the last balance
last
that you
agreed.
did agree to.
Okay, the last agreed one. Okay, thank you very much. I think I'm starting to grasp it a little bit more, but as you understand, I'm a little bit far away still from what might be optimal to use it. But thank you.
No problem. The host has, in the meantime, informed me that he had to move to the next engagement, and I do think it's just the four of us. So yeah, if you have another question, I'm happy. But how about I close the recording? I can't actually close the recording. That's too bad.
I didn't want to monopolize because I was monopolizing too much now, just to really understand it. But if you don't have any other questions, I think you understood a little bit of where was my weakness and lack of understanding still, in terms of understanding this overlay and let's say how it forms on top of the let's say the main blockchain that would be the Bitcoin.
Yeah, I would have to say the paradigm is completely different. You know how many Bitcoins a particular address has, and everybody agrees about that because they can inspect the ledger and make that determination for themselves. Whereas on Lightning, the only thing you care about is that every channel you have with everyone else, that there is consensus in that channel, and you don't care about the rest of the network.
Mm-hmm.
And if there is disagreement in those channels, then you settle there then and there using the Bitcoin blockchain.
So it's always one-to-one.
Yes. Well, there are extensions to many parties.
Yeah, okay. I think I'll have to digest your presentation and try. You're going to make it available again? Sorry, make it available so that I can see it again.
So there was recording. I do think the recording dropped out for 20 seconds or something, but the recording is still on. So yes, I expect there will be a recording, but I'm not responsible for producing that. So it might be. I think it'll be on YouTube or something like that, but I don't know the details there.
Yeah, I think I'll have to see it at least 2 more times, and then I'll try to digest the mathematics there. But I thank you very much. I think it was good. At least I understand it a little bit better now, but I'll still have to digest it again, the details. Thank you.
No problem.
Pleasure. Great work. Clearly advanced stuff, but great work.
All right. In that case, I will be going home. Goodbye, everybody.
Goodbye.
Ciao.